So let's welcome our last speaker in this application session. This presentation is going to be again like the first one, more from the area of scheduling. So we are moving to the area of healthcare. We are going to hear about the problems with uncertainty, and Chen is going to present the paper. Please.
Okay, thank you. Hello everyone. Today I'm going to present on the work scheduling for healthcare visits with duration uncertainties. I'm Chen from Singapore Management University, and this is a joint work with Zach and Steve from CMU and my advisor Hoong from SMU. So home healthcare actually provides a range of healthcare service that is specially delivered at patient's home. This kind of medical service range from cleaning, personal hygiene to some medical treatments such as taking the blood pressure, injections, prescriptions, and so on and so forth. Over the past decades, more and more people are choosing home healthcare, especially for patients with chronic conditions. According to U.S. National Association for Home Care and Hospice, roughly 12 million people received home health care service from over 30,000 providers in 2008. This is a large number. And against the manpower crunch in home health care providers nowadays are under increasing pressures to provide high quality service to patients at low cost with the increasing demand coming from the aging population. Current home healthcare scheduling rely mostly on healthcare providers manually communicating and negotiating with the patients over the phone. And this is usually the case, at least for the case for our partner companies. And however, this process is very costly and inefficient and often myopic, as the scheduling process is not well coordinated among the different providers, especially when the number of requests is huge. So it's very important for the healthcare provider company to optimize their scheduling process, to design a better scheduling mechanism to schedule visits in an optimized fashion, subject to a complex set of constraints that are arising from the company's needs. So the objective here is to schedule and route service provider for home healthcare visits on a weekly basis that consider the needs from both the patients as well as the service providers. So when we actually take the real consideration from the company, which is a local company in Pittsburgh, and we focus on generating the actually the proactive scheduling that actually generates the start of the day schedule for the coming weeks. Here's the inputs and the outputs. As for the inputs, we have patient's preference and weekly requests. So information include, let's say, the patient's home locations, the preferred providers, service time windows, service requirements, as well as duration, and so on. We also have requirements from service providers' perspective, such as providers' depot locations, providers' qualifications, and availability time windows, and etc. All these informations are very important because we have to match the right providers with the right patients on the right timing. And we actually, a request is considered as completed if and only if a qualified and available provider actually serve this particular patient at the time that he specified and stay with the patient for the whole duration. We also have the workload fairness threshold as the input for the workload constraints, and we have the uncertain travel and service durations. Here we assume the duration follows certain distributions as the proper input, and actually our model can handle all kinds of duration, but in the presentation later, in the experiments, we actually focus on the normal distribution. And for the output, we have the routes for each provider on each day. So the problem is further subject to the following considerations. First, a patient can specify several time window options for a single request. A time window actually specifies the duration that this request has to be started. Let's say, for example, you can specify something like 3 p.m. to 5 p.m. on a certain day. And multiple available time windows can be specified for the same request because sometimes patient may be available on different days for a single request. And a patient also can put up several requests over the same week. And this request can be temporal dependent, that request Y has to be served at least like 3 days apart from the last visit, and or at most 5 days difference. So there's a visit dependencies among the different requests, and it's very important to incorporate that because it's commonly observed in the healthcare industry. And we also have the workload considerations from the company. As the provider is paid a fixed salary as long as he's working on the day, the healthcare company actually prefer the provider to work more than 6 units of work, and which is a soft constraint in the sense. And at the same time, a maximum workload is imposed to prevent overworking for the providers. And we also consider the continuity of care. This is often seen in practice, which basically says that the consistent primary provider is preferred for the patient. This is important for patient satisfaction because, especially for patients with chronic condition, they prefer to be served by the consistent providers. And lastly, we also want to incorporate the uncertain duration, both in terms of travel as well as the service. In a real-world scenario, travel and service duration are usually uncertain. As you can see, due to the varying healthcare condition of the patient as well as the different experience of the providers, this service duration can vary significantly. As you can see from the figure on the right, we actually grouped the service duration by different types of requests, and we can see that the red bar represents the service duration and the blue line represents the standard deviation. The standard deviation can be as high as 30 minutes. And in addition, for the travel time, because there are some unforeseen travel conditions such as congestions, breakdowns, may result in a various travel duration for the same traveled destination and starting point. So it's very important to take into consideration of the uncertain duration, uncertain travel time as well. However, existing work fell short in the following 2 key aspects. First, they fail to address the duration uncertainty. As far as we know, there are only 2 works talking about the uncertain uncertain durations. The first one is only focused on single-day scheduling for home health care. The other one can only solve the instance up to 75 patients and 22 providers. So it's rather not realistic for our case. And the current work also cannot address all the business requirements raised by our problem. So in this work, we actually model the problem as a variant of a combination of the assignment plus orienteering problem. So more specifically, the team orienteering problem, whose goal is to determine routes for a team of agents that maximize the total reward collected. And here is just a graphical example of the problem we have. And as you can see, we have a set of providers and we have a set of patients' requests over the network. And the provider can have availability information, qualification information, and requests can have like time windows, reward, displaying, and etc. So formally, we model the problem as a chance-constrained integer linear programming model, and the goal is just to maximize the reward collected by the whole company, considering the route penalty. And here we use the request provider dependent reward to factor in the continuity of care. That is, if the request is assigned to the primary provider, it actually gets higher reward. And if the request requiring more units work, the request is more important, it gets higher reward. It's a linear combination of the different components in the reward function. And as for the route penalty, we say that if a route contains less than 6 units of work, this route actually incurs a penalty, and this 6 units work is actually a figure that the company gave us. So we have a set of assignment constraints for the providers, which basically says like the request can only be assigned to at most 1 provider. It cannot be assigned to any unavailable or unqualified ones, and there's interdependency constraints between different requests for the same providers, and there's workload considerations. A request can only be assigned when it can be visited, and this constraint actually bind the decision variable of y and x together. This is the set of global constraints in our model. And we also have a set of provider day level routing constraints for each provider on each day. Those constraints are local constraints for each provider's route on each day, and the constraints are independent of other agents' route for different days. And for most visibly, we have constraints to ensure the flow consistency, to initialize the start time for different providers, and we have the timing consistency constraints to ensure the route is consistent. And recall that we have talked about the uncertain durations. This duration only affects the time window as well as the time budget constraint for each provider on each day. So thus we model this all this uncertainty by time window and time budget chance constraint. So the chance constraint actually enforces that the probability of satisfying the respective constraint is greater than 1 minus alpha, where actually alpha here is the threshold, is the risk threshold that indicating each decision maker's level of conservativeness. And since this problem is well structured with only one set of global constraints that binds the decision variable, binds the assignment variable y with the routing variable x, and the rest of constraints are routing a local provider day level routing constraint for each provider on each day. So by observing this, we actually relax this constraint into an objective function using Lagrangian relaxation to scale up the solution approach. And the idea is actually to relax this global constraint into an objective function and penalize the violation of the constraint by using Lagrangian multiplier. So Lagrangian relaxation actually approximates a difficult problem by a much simpler dual problem. Okay. The resulting dual problem can be solved using. After relaxation, we further explore the separate structure to decompose the problem into much smaller subproblems. In the end, we have one assignment subproblems and several provider day level routing subproblems. And this dual problem can be solved by subgradient descent algorithms, and because this is an iterative process until convergence or termination condition met. At each iteration, we're actually solving each subproblems, and by the end of each iteration, we are actually updating a master function. So during the iteration, all these subproblems can be solved in parallel if we really want to go into the real-world implementation, and we are able to get solution, quantify the solution quality by duality gap. So we also take up a few steps to improve the scalability. For assignment subproblems, we have an ILP formulation which can be solved by SCplex, and we also try the linear relaxation. And for provider day level routing subproblems, we develop a breadth search with dominance pooling. We actually explore the search tree and define a dominance property for the routes and cutting the unpromising branch. So from that, we can easily, so two feasible routes having the same set of nodes with different visiting sequence and the same ending nodes actually leads to the same objective value and providing a fair starting point for further route expansion. So from that, we can easily find the dominating routes, and the intuition is that routes of much shorter time will have more room for future insertion. And further, we handle the chance constraint by sample average approximation techniques. And basically, we randomly generate a set of samples from the known distribution. In the search procedure, we check whether the time window and time budget constraints are violated. So by doing that, we are able to generate proactive route schedules with risk control, feasibility, and optimality. And also, for the primal extraction is to restore feasible primal solutions from the dual solutions. We have ILP formulation for that as well. We also develop a greedy local search heuristic for that. So here's the data set we used for the experiments. We evaluate the performance of our proposed approach on instance adapted from the real-world data set. It's a 1 month data from 2015 September 21 to 2015 September 27, and we have all this patient information, visit informations, and we adapt two set of instances from the actual data. So we have deterministic instance as well as the stochastic instance. So for stochastic instance, we assume that service and travel durations follows normal distributions. And here is the experiment results. So for the deterministic case, we first compare our deterministic approach without the sample approximation to handle the uncertainty with the actual schedules. And in the first experiments, there's no inter-visit dependencies to compare with the company's current actual schedules. So we actually observed that it outperformed the actual schedules on the solution quality significantly, especially for the objective functions. And we have more primary provider assigned with less route generated, which means that less manpower is required. And we also demonstrated the solution quality for the deterministic approach with for the scenario with multiple time window options and inter-visit dependencies. And we can observe that we are able to obtain solution within 6% optimality gap, and our approach actually can solve quite efficiently. So for the stochastic scenario, we actually compare our approach with sample average approximation with our deterministic counterpart, and we evaluate the approach with two sets of duration input, the max and the mean and max durations, and the results average of all the instances and evaluated over the 1,000 realizations. So in the result, we can see that we are able to hedge against uncertainties, and our approach actually achieve high expected objective value with almost no violations. Well, for the mean one, although we can have high expected objective values, but there's a lot of time window violations. For the max duration approach, obviously there's no time window violations, but the expected objective value is very low. So as for the future work, the current model focuses on maximizing the total reward collected by the whole company. However, there's also other objectives that can be further explored, such as minimizing the distance travel, reducing manpower, maximize the service level, and also we can incorporate more additional considerations, such as lunch breaks, task synchronization, whereby a task needs to be served by multiple providers at the same time, and also the uncertain duration is also important. Uncertain demands is also important to incorporate, because sometimes patient may cancel the request last minute. And also the current model focus on single modal transport, and however the needs to combine multiple modes of transport or sharing the resource are often observed in real life, especially for urban cities whereby the public transport system is very convenient and the vehicle resources are limited. So we can also extend our model for that. And that's all for my presentations.
Questions, comments?
How are you getting the optimality?
Because we are using Lagrange relaxation, so we can actually get a dual solution as well as the primal solution. So with that, we can estimate the optimality gap.
What's the typical size of the programs in terms of number of visits?
Okay, so the instance we are presenting here actually has 2,000 requests and 200 providers. So, which is rather a large instance compared to the existing ones.
This is a static problem.
Yes.
But in case you want to solve a dynamic version of the problem where you have a request, online request, do you think it's difficult to update this model or not?
The current model is a proactive scheduling approach, which is an offline approach that's scheduled for the next week. So it's not an online approach, and we are also interested in exploring in that direction, because surely there will be some cancellations, demand changes when it comes to the actual execution.
Yeah, just to follow up on that, we are developing and have developed the constraint-based search technique for the online scheduling. this you take this as an initial scheduling technique, and then we load it into the SDN, and we process updates as they come in, handle them incrementally.
So it looks like that, let's say, application in the practice still needs some additional work, or you mentioned some future work, so it's like
Yes,
there is still some work to be done before applying it, right?
Yeah, it's
Yes.
currently being in a sort of a pilot setting at the local company.
So thanks to the speaker again.